Now?
Yeah.
Yeah. Okay. Good morning, everyone. And as he said, I'm Macias. I'm from University of Coruña, and I'm going to tell you about a recent experience that our research group was involved in. And because we can think that it could be interesting for the functional programming community. So, beginning, why are we here? Well, it's an obvious question and an obvious answer. We love functional programming, and in particular, I love, and our research group loves Erlang because it helps us to build robust, fault-tolerant, and distributed systems, and Erlang does it very well and very easily. So we have the programming language is just a tool to implement systems, but it is us who implement the requirements of the systems, and we all know that the system requirements change over time. And this is a very annoying problem for every developer, isn't it? So we have the initial requirements for a system which fits into Erlang perfectly. We implemented it using Erlang, but we have to face with unexpected conditions that when we are designing the system we can't expect. In particular, I am talking about net scripts and node failures. So after checking the deployment scenario, we redesigned the system to manage these unexpected conditions and implementing the proper contingency mechanisms to deal with it. Finally, the system went into production, and nowadays it's running 24/7 with about 100,000 users. And I'm going to tell this story. So I'm going to follow this outline. First, I will talk about the system requirements and the problems we found at the deployment, and then I will talk about the relying idea and the solutions we implemented, and finally some conclusions. So the system we use as case study is called Advertise, and in this picture you can see the system architecture. However, this is not the important thing today. And we just need to know that Advertise is a distributed system for advertisement transmission to a customer home set-top boxes over a digital TV network of a cable operator. So, Advertise system has to ensure the proper coordination of the advertising mechanisms. I am talking about, for example, the system must receive the advertising campaigns, has to process them, has to record the initial date and the end date of each campaign, record the channels in which the advertising will be shown. The system also has to be prepared to send advertising signals to the STVs in a specific period of time. For example, if the cable operator wants to send an advertise to any STVs about a new promotion and during all the month and at 10 p.m. then Advertise must send the ads in that specific moment. And finally, the system also has to record the number of displays of each piece of ad, because we want to provide statistics to the customers. So our major challenge, however, was to manage the size of the communication network, because the client has about 100,000 users, and this was the system must serve ads to all the users potentially at any time. So we implemented the system and we tested it and check if it satisfies the client conditions. And in this box you can see the development scenario in which we test the system. The most important thing is the first item. We tested it using 3 different physical machines, each one with the specifications we can see in the slide. So we simulated STVs arriving to the system, interacting with it, and we state that advertise handles about 140,000 STVs properly, so with a CPU use about 10%. So as I said before, a client has about 100,000 systems, so we thought at that moment that we had got it. However, when we deployed the system, we found a very, very different scenario. Instead of deploying the system over 3 different physical machines, our client thought that this was not an important requirement, and they enforced us to deploy the system over 3 virtual machines. But not only this, these 3 virtual machines are running on the same single physical machine. And not only this, they use a shared hard disk drive. And not only this, in the single physical machines there are other virtual machines with other applications which use the shared hard disk. So you can imagine the very big difference between the two scenarios. So these famous physical machines have these specifications, and here you can see a quick comparison between the 2 scenarios, where the 3 first rows are which make the difference between the two stages. So testing the system in the deployment scenario, we found that it only handles about 40,000 STVs, and there was an unexpected behavior of the system. Sometimes suddenly the application stopped, and there are no apparent reason for this behavior. And sometimes the memory use shut up and the operating system killed the application. So, analyzing this problem, we realized that the problem was the network unreliability, because the problem was that the frequent saturation of the shared resources were seen by advertised nodes like short network partitions, and this produced a cascade of failovers, and finally the application stopped entirely. So we have to deal with the problem that when a network partition is produced, one node loses its connectivity. There are two points of view depending on the actors we are considering. For example, from the point of view of the isolated node, the other nodes fall down and it assumes all the system functions. And on the other hand, from the point of view of the other nodes, the isolated node fall down and they distribute the control. So when the network recovers from this situation, we have a very big problem, because there can be inconsistencies between the 2 datasets handled by the 2 groups of nodes, and something which is worse. That is, there can be duplicated responsibilities. For example, functionalities that must be unique in the whole system, suddenly they are duplicated in the 2 groups of nodes. Speaking in Erlang terminology, we have global names duplicated, and this produced a random killing of the processes, overflow, and then suddenly the supervision mechanism stopped, and finally the entire application. So the nasties were seen by advertised like a node failure, and in this situation we have to think about which property we want to preserve in a distributed system like advertised. There are a theorem which is called CUFP theorem, which states that in the presence of network partitions, only one of these 2 properties must be preserved. We are talking about, we have to choose between consistency or availability. I mean, we have to think, what is more important for a system like advertise? Trying to preserve the consistency of all the data all the data must be updated at all time, or in the other hand, we can send to STVs data which is not updated, but we ensure that the system will reply always to the system at any moment. So in this case, we selected consistency. And we selected consistency the first option because we could not afford that advertising campaigns were corrupted, because advertising campaigns are products that the advertisers pay for. However, we can afford that in a specific moment an ad will not be sent to an STV because the ads are shown in the TV while the user is surfing in the menus in the interactive application. So the user will not notice anything if a specific ad is not shown in a specific moment. Then the solutions we designed to preserve the consistency of the system is, we can read it in the box. It's one node loses its connectivity and finishes itself alone, immediately suspends the execution until the network was recovered. However, it has the side effect that if all nodes in the system step 1 fails, that node will protect itself and the system will not be in operation. So to ensure a basic fault tolerance, advertisers should be run in a cluster of minimum of 3 nodes, which fits with the deployment scenario we have. Finally, as I said, the advertising system is into production, and is running on 3 virtual machines. Now it's handling about 18,000 STVs per node, and with peaks of 23,000 STVs. And the same tests we run in our development scenario, we run with this version of advertise, and we reach a max of 45,000 STVs per node. And our client now no reported us any problem in the last 4 months. In this slide you can see 2 examples of advertising campaigns. The first one was the longest campaign in the system. It dured about 2 months, and the ads were displayed over 66 million times with a peak of 140,000 in a single hour in prime time. And the second example is only to show that we can set different parameters of the campaigns to segment the advertised to a specific user. For example, an advertising campaign of any STVs on working days from 7 AM to 12 AM in 6 channels was displayed about 460,000 times with a peak of 29,000 in a single hour. So the conclusions of this experience and of this work is that we selected Erlang because it seems a good candidate to implement distributed systems, and we applied and we used functional programming in a very specific area like dealing with a digital TV network with a growing number of users. And the advantage of Erlang, of using Erlang, is its concurrency and distributed mechanism, the message passing, the links between processes which provide fault tolerance, and obviously the functional power. However, we have to think that when we are implementing distributed systems, we have not only to think about the system functionalities, we also have to think about some kind of unexpected problems like the network topology, and the network security, and we have to deal with unexpected problems. Finally, the disclaimer. This is a specific problem with a specific solution to this scenario, but if, for example, we have to preserve availability over consistency, this surely will be a very different story. Anything else?